So today the first presentation will be by Dr. Vinod Kumar from MRC LMB. He did his PhD in Max Planck Institute, isn't it? In Frankfurt with Werner Kulbrandt, and then he mostly did work on 2D crystallography, and also he started off with single particle cryo-EM. And currently he is he's working along with Professor Richard Henderson in MRC LMB, and he is working on single particle cryo-EM methods. So he will be starting off with one of the most important topic, that is determining the 3D orientation of single particles. And both the topics are very important today. And the second topic will be by Elena Arlova, who will be talking about methods in 3D reconstruction, resolution, and FSC. So I would like to invite Vinod. Okay.
The title says Methods in Orientation Determination. I've nicked a lot of slides from one of the courses which was held in LMB. So if in case you find mine boring, you can have a look at the course which is freely available in the net. Also, there is also movies of the speaker speaking. So if in case you find me boring, you can have a look at this. Anyway, so you have been going through this step by step in the past 5 days. So now you know how images are formed, what you need to do because of CTF, because of the stone rings, how you estimate and how you correct particle picking and class averages. So now we are here at this point here where our goal is to increase the signal to noise in each particle images. So that's we generally call 3D refinement. It involves a lot of different steps. And for this, you need an initial model, which will come tomorrow as a separate lecture. So we assume that we have a model already. Then after 3D refinement, you can do classification, or classification can come before 3D refinement so that you start up with better particles. And then, of course, you go to map interpretation and you can publish the maps. So when I mean 3D refinement, you start with a micrograph. Here is a micrograph of complex 1, which is a membrane protein complex. And then you get reference-free 2D class averages, which shows different views. And then the next step, where you determine the orientation of each of these particles, you refine in steps so that they get better. And then you reconstruct it, then you get a 3D map. So this is a very critical step and determines whether you will get a high resolution or you get a low resolution or you get just a blob. So this is a slide which I took from Tony Crowther, who is at LMB. So any 3D specimen, you get 2D projected images, and when you do it Fourier transform of these 2D projected images, these are related to this 3D object by sections of 3D Fourier transform. So which means that if you stack up all these together and do the Fourier inversion, then you get a 3D map. So this will keep coming up in the lecture as it goes. So it's critical to remember that the 2D Fourier transform of the projected images is related in Fourier transform to the 3D object. So you can read this review in Methods in Entomology by Pavel Penchak. It's very useful. There are quite a few of them. And the goal of 3D refinement is to determine how this projection relates to the 3D object. So we need to determine 3 Euler angles and X and Y shifts. So the more accurately you determine them, the higher the resolution will be. So this is the basic of 3D refinement. And so the 3 Euler angles are phi, psi, theta, and then X and Y shifts. So the way we do is that you have a initial model, which is shown with this object here. And then you generate projections using computer of this model, and then compare it with your experimental images, which are again projections, and then you give a score. So once you have that, then you can invert it to get a map. So you iterate this to get a higher resolution map. So however, in reality, the cryo images are very noisy. That's because electrons are very, very potent, and they damage the biological material, which is mostly made of carbon. So in few seconds of exposure, you just get as of broken carbon. So we use very low dose, which means that you have large amount of noise in the images. And then we need defocus to get contrast, which means you get artifacts from CTF. If you had a very good faceplate, you don't need to defocus, then this problem will be solved. So you may hear later in the week that there's a new faceplate which apparently is very good enough to get away from this. And the last one is we don't know how the particles fall on the grid. So you can have different orientations, you can have unknown number of classes, you can have heterogeneity, and so on. So SARS calls this mathematically inverse, incomplete, and ill-posed problems. So these three problems which are associated with EM images in general. So I will go through one by one and then explain how we deal with it. So inverse problem. So a forward model, which means that if imagine you have a PDB of known structure, you can convert that into your map, and then you can model for the CTF. Then you can apply a projection operator, add some noise, which is very difficult to simulate computationally. But if you can do that, then you can simulate the experimental images that you get from EM. And this is relatively straightforward. In fact, we do have a program at LMB, which we call SPEMS, Single Particle Electron Microscopy Simulation. This is written by Greg McMullen. And whenever we start a new project, if we had a PDB, then we just use that to convert to a map and then try to simulate using different voltage or different defocus or different electron dose how the image should look like in different projections. So this is very useful and it's very easy. However, to get the volume from the experimental images of EM, which are very noisy, is very difficult. That's we call inverse problem. And incomplete data problems are those because we don't know the orientation of each of the projections from the images, and we don't know the classes they belong to. And these are difficult to solve, but we can iterate in cycles to get very high signal-to-noise ratio, and then we can assign the orientation and class assignments. Sorry. Wow. Yeah, so if we know, if in case we knew the orientation and the class assignment, then it becomes a complete data problem when we could solve it easily. So since most of you are crystallographers, you may know that when you shoot a crystal on an X-ray beam, you get intensities, but you don't have phases. So to get phases, you need to do something else, like heavy molecular replacement or heavy atom soaking and so on. So if in case those intensities came up with a label saying there is the phases, then it will be an easy problem to solve. Something similar we have, because we don't know the orientation, we need to determine it. So that's called the incomplete data problem. So here is an example of noisy image, which is underlying images of a penguin. So these are the observed data, which are images, and they are in different orientation. So the missing data are orientations. So we have to determine this, without which we can't average and get the underlying structure or signal. So this is not an easy problem. If we knew all the orientation beforehand, then all we need to is calculate the noise and then estimate average and get a very good map. So this is kind of very easy. So how do we overcome these incomplete data problems? So we add Y, which is the possible rotation and shifts into the model. In one way, here we add this, and then we try to find the single best match between the experimental image and the reference image. Or in another way, we can marginalize over Y, which means that regardless of what Y, we can calculate a probability of all possible orientation and weigh them and get the best weight. So this is called maximum cross correlation or least squares. This again you may know from crystallography, and this one is called maximum likelihood. So there are hidden parameters, which are the orientation, which we are marginalizing in maximum likelihood. So the maximum cross-correlation approach is very common in EM. So the way it works is that you have a reference image, and then you have a experimental image, which is in a sideways view here. So we start with comparing this experimental particle to the reference image by cross correlation. So you keep rotating. So our brain is very clever than the computer, so it can tell you just have to rotate it, counterclockwise 90 degree, and you will get the same. But the computer sees only the pixels, so you need to give mathematically some form of weighting to tell the computer what is good or what is bad. So then you rotate, and then finally you will get a match. And this you can plot as a cross correlation against rotation, and you get a best peak here. So this is used in getting a further better map. So this is shown here. So you start with the random oriented particles, and then you align. You get, this is not perfectly aligned, but you get a better map. Then you can use this in the second round of iteration, and then you get a better map. And this is how the cross correlation works. So in contrast, the maximum likelihood approach, which was first proposed by Fred Sigwerth in 1998, this was for just alignment, not for classification. So again, you start with a reference image, and then you have an experimental image, but then you add a statistical model, which then works like this. For each of these experimental images, then you tend to calculate the orientation in all possible rotations. So for this example here, where the penguin lies in a sideways view, you can see that it's very transparent. There is no correlation. But this one is more closer to what the reference image looks like. So this gets more weighted. But the other one here is the upside down view of the penguin. So you will get also similar, not the equal weight, but something of a lower weight. The important thing to note is that all these rotations will have non-zero probability. So there will be always some kind of probability. But as the iteration goes, then it will tend to pick up the best one. So this again, you iterate, and then you can assign better orientation, and you get a better map. So that's the difference between. Okay. So the important thing is that if there is too much noise in the data, then the maximum likelihood doesn't assign discrete orientation. What I mean by that is that, so in a typical good image, as if you want to say, then you get a very nice peak. Then you can say this is the orientation based on the cross correlation. But however, if the images are noisy, then you get something like this, where there is no discrete peak. So in maximum cross correlation or the least square, it's possible that some of them are assigned, and then they get stuck in that minimum, and it's very difficult to get out of it. So in maximum likelihood, it doesn't assign. It tries to keep this as kind of equal weightage. But as the iterations improve, then it tends to, hopefully, it tends to find the best peak. So these two methods are kind of, you can say they are very similar. If we don't have a lot of noise in the data, then they are equivalent, and you can just use maximum cross correlation or maximum likelihood. However, because we have a lot of noise, we at the LMB prefer maximum likelihood for refinement. So if you want to read more on maximum likelihood in comparison with cross correlation, again, this methods in enzymology in 2010, which has a lot of chapters dealing with different topics, is very useful. Okay, we come back to projection matching, because the ones which we were discussing was mostly on alignment, not on refinement. So again, we start with this 3D initial model. You generate projections, and then you compare this model with all different projections. So here, there's a picture of a boy, which is Source's son. And then you find, for this experimental image, the best maximum cross correlation. And then you keep doing this for these two. And then when you do the 3D reconstruction, you tend to get a underlying signal, which is of the boy here. And then you refine, you get the orientation better and better, and eventually you should be able to see the real image which is lying under here. So that's the basic behind projection matching and how you iteratively refine the orientations and get a better maps. So in maximum likelihood, instead of giving instead of finding a single peak, you give for each of this experimental image probably weighted angular assignment. So each of them has different one, and this, for example, this one has the highest weight here, and then these have lower ones because it can't distinguish between these two here. So, but as the iteration or the refinement goes on, then it will be able to distinguish these two. So that's the difference between maximum likelihood and cross correlation. Again, if there is too much of noise, the program itself will not allow you to make hard decisions. So that's a good thing about maximum likelihood. Okay, so all these programs are local optimizers, which means that there is a minimum which it gets stuck. So this is very common in most fields. And we need an initial model, which will be discussed tomorrow. Most times, if you start with the random angles, for example, if you start with sphere or any random angle, it works well with two-dimensional classification. But however, for 3D refinement, it doesn't work that well. You may get so if you had a bad model in, you will always get a bad model out. So in particular, if you use a common lines method to start with the projections which are derived from images, and if you had a bad model, then again you will get very bad model out. And there is another way of getting an initial model, which is stochasticity, which means that instead of getting this stuck in the local minimum, you can make it jump. It's similar to what you do in simulator annealing in X-ray. Then you can potentially reach global minimum instead of local minimum. In these cases, you can define from random blobs. So you can find the application of stochasticity in Simple, which was written by Hans Emlund, and E-Man, which is written, of course, you know, because you have been hearing from him for the past 2 days. So one of the problem is that, again, you can refine anything from anything, which means that if there is too much of noise, you're going to get a bad model. So you have to be very careful on any of this. So far we have been talking in real space. So now we go to Fourier space. And one of the most important thing is that you need to correct for the CTF. So this is an example showing what happens if you don't correct for the CTF. This is a 2D projection class averages of beta gal, which we use commonly as a test object. So this image is not CTF corrected. So in any of the program, you can just turn the CTF off, then you can see a halo around the molecule, and the background is kind of gray, and then you don't see any features. But this is CTF corrected, then you start seeing features already in 2D class averages. So this is a picture of Max Perutz, again illustrating the same thing. When you CTF correct it, then you can start seeing fine features in the image. And if you don't do it, then you tend to have a lot of non-native features. So that's why we need to correct for CTF. Again, back to the projection slice theorem. So because we are in Fourier domain, just remember that this 2D Fourier transform are sections of 3D Fourier transform of this object. So the data model in real space and in Fourier space is that the difference is that you convolute with the CTF in real space, but in Fourier space you multiply. This is much more easier than what you can do with in real space. And then you take a slice of this projection. And the noise model, which is described in real space and Fourier space, is different. In here, it's called white noise, and in Fourier space, we call it a color noise. So this is again coined by Source. So what it means is that, so this is the experimental image, and then you have CTF, which gives some artifacts. You multiply that, and you get certain noise. So this noise is actually over all the frequencies in the Fourier space. So what you can do is you can determine resolution-dependent noise model. Because at lower frequencies, the noise is kind of lower, so you can you get higher signal, but higher frequencies, the signal is low, and you get more noise. So you can determine and depending on that, you can, based on the resolution, you can get a very good noise model. And you can determine this noise for different groups, which means different micrographs with, say, certain defocus, and then you get different values. So this can be used in the program to determine the noise accurately. So the last one, so we know what an inverse problem is, and then incomplete problem, ill-posedness. What it means that the experimental data is not enough to determine solution, which means that although apart from the noisy images, if you give any data, there are too many noisy reconstructions that describe the data well, which means that it's very easy to incorrectly interpret the map. So what can we do about it? So the way we can do is we can use something which we know as a prior to solve this problem, which one's called regularization. This is very common, what we call low-pass filtering or Wiener filtering. So the way it works is that you have a model, and then you have the experimental images, and you align and reconstruct. You get a noisy reconstruction. So if you ignore this filtering, and if you just keep iterating this cycle here, then the noise builds up, which means that the resolution what you estimate is going to be lower, and then also you get in the map some of the features which are not true. So what then people do is low pass filter the map at every iteration, and then that's because the map or the model which is underlying is connected by atoms. So in low resolution, they have a very smooth feature. So that's what you do, a low pass filter the map at every iteration, and then you go through. So this can be implemented in different ways. And previously in the past 10 years, this has been done kind of trial and error. So it's left to the users to determine how you low pass a filter or how you apply the filter, which results in the user determining, which is a very bad thing, because if you don't know how this exactly works, then it's possible that you get something which is not true. So what Schwarz did in 2012 was to use a prior, which is again the smoothness of the map, as a parameter to determine this this low pass filtering or Wiener filtering. So what now we have is a posterior and a likelihood which comes from the maximum likelihood of orientation, and a prior. This is what he calls rely on regularized likelihood optimization, which you will learn today in the afternoon. So in the likelihood, we assume that the noise is Gaussian and independent, and then you have a spectral power over the whole range of resolution zone, which we call the colored noise. And the prior is, again, signal is Gaussian and independent, and the smoothness in real space, this is what I described as the model being made of, say, atoms which scatter the electrons in space differently. So that's the smoothness in real space. So then you get this formula. You don't need to worry about any of these formulas. If you're interested, you can read in the papers. So the only thing you need to remember is that in rely on the signal and the noise is determined from the data, and this signal and the noise is then incorporated in this formula here in the noise and the signal, which actually learns both of these from the data and then used for CTF correction and also for 3D reconstruction and 2D class averages. So in rely on, you have this alignment, which is the expectation step, where it determines all the possible orientation of the projection of the experimental images. So the sharpness of this determination is determined by the noise. Again, the noise is read from the data, and then you have the smooth reconstruction, which is a maximization step. So this goes in circle, and then you get a reasonable structure. So to summarize, in 3D EM refinement, we have three problems: inverse, incomplete, and in-pose, and we can deal with each of these by iteration, marginalization, or regularization. So in rely on, all these things are done in a single function, you can do 2D, 3D class average, and 3D refinement. One of the more important thing is that the program learns from the data all these optimal parameters, so the users don't need to do a lot. So taking a lot of control out of the users makes things much more reproducible, one could call it. So I just thought I will put this slide up. So there are a lot of softwares which you can use. There is EMAN, which you use. There's FreeAlign, which does only refinement and reconstruction by conventional maximum cross correlation. But in classification, it uses maximum likelihood. Then you have eMagic, which you will learn tomorrow, Friday, and then later. Then Spider, which I think is not being used by a lot of people now. But you have SparX, which is, I think, a derivative of Spider. And then you have XMape and Relion. These both use a lot of maximum likelihood because SARS wrote both of these. And then you have Simple and Prime, where you just give images and the pixel size, and apparently it can give you a good structure. So, and then BSoft. So one important thing to realize is that you need to know at least one or two of these programs, because not one of these programs is going to give you satisfactory results. So it's always good to have an idea of how different programs work, and then you can just switch between programs and try to. For example, if you try to do a 2D classification in Relion for a very noisy image for a small particle, then you will find that the classification is very poor. So it's always better to go to eMagic or eMan to get an initial idea of how good the data is. So this is something you need to remember, not to ignore that, because Relion is easy. There is a temptation to just use that and ignore all others. So it's better to learn a few more. Okay, so those were the theory and how the program works. I thought I will also include some of the practical problems which you might encounter when you do the 3D refinement. So these are some of the things which I put here. Overfitting is one thing which is very common. You might have heard from Steve already. And then the question you want to ask is my refinement improving? So you can say, collect a lot of data, you put it in the computer, and then you go away and come back and see if the refinement has improved. And then how many particles do I need to get for a given resolution? So that's something. And then you keep adding particles, but the resolution doesn't improve. So why does it happen? And then the orientation, distribution, and validation. So what is overfitting? So this is an example of a virus, a normal test specimen. It's taken with a direct detector. So I mark the real particles with blue here, and the neighboring, what I call noise, is the eyes in red color here. So I tried my best to actually refine noise. This is how you get. That's the real particles. Blue circles give a very nice map. And this is my best, what I get as a map. This just shows that the programs are getting better, so even if you give noise from the background, you don't get. So my best attempt was using FreeAlign. I tried, and maybe you get a kind of an overview of this molecule here. That's just from noise. So this is just to remember, because if you are doing autopic, and if you give a lower threshold, it can pick anything. And the worst thing that can happen is that not getting this kind of map, but some of the noise particles can end up in your data set, and then they will result in lower orientational accuracy or in resolution. So that's the thing to remember. So this is a picture from Richard Henderson and co-workers who kind of devised a method for validating the resolution. So this is called high-resolution noise substitution or phase randomization. The idea behind it is that you have a micrograph, so you can pick particles which are, you pick particles, and then the neighboring areas are noise, which is eyes, and then you kind of you have the noise regions, and then you randomize the phases beyond certain resolution. So if you want to claim, for example, you have 10 angstrom, then you randomize again beyond 17 angstrom and see if the signal is true. Or if you want to claim 5, then you randomize around 10, and then you see. Then you refine both these randomized particles and the raw particles, and then you get curves like this. So these are 4 different programs which were used in that paper to calculate how much noise, how much noise is refined during refinement. So this is Relion, where, as I will tell you in the next slides, here after randomization, the FSC curve drops completely, and then you have the real signal here. So this is a program which was meant to do overfitting deliberately. So you see that here, the blue curve, which is the randomized one, it goes up and it goes all the way to 5 angstrom, which is obviously nonsense. And then you correct for this, and then you get a real resolution, which is 6.5, comparable to Relion. So these are other two programs. Again, you can randomize at different values and see how far your signal goes. So this was important because in the old days, you could refine anything and you get a resolution estimate. But nowadays with detectors, you start seeing side chains and maybe ions too. So then now you can't see it. If you want to claim 4 angstrom, then you have to show features that are really 4 angstrom. So the way Relion, or again, gold standard, not many people like it, but the way it works is that you split the data sets into 2 halves. That's from the beginning. So previously what was happening is that you took the whole data and then you refined, and then before you estimate the FSC, the data was split into 2 halves. So they were not really independent. But in the case of Relion, it already splits into 2 halves, and then you align reconstruct, you calculate a gold standard FSC curve based on what I was telling about regularization. Then you filter based on this, you iterate, and then once it converts, then you calculate a whole set of reconstruction. So these are some of the examples which was already reported in sources paper. So he did 20,000 simulated GROW-EL particles. So this is not from the real data. So these are simulated in computer. And then these are the experimental particles. So you can see that there is some resemblance to experimental particle. So when you do a conventional projection matching, which is you don't divide the data set into 2 halves, but you use all this data here into for a refinement, then you get a resolution of about 4.6. But in reality, the map is really 7.8. So that's because somehow the noise is building up during this refinement, and then it gives a resolution which is not true. And one of the things to remember is that Peter Rosenthal and Richard Henderson in 2003, they devised what they call what one should report in as a resolution. So if you had a 2 independent half data, so this is important, 2 independent half data sets, which means that the data sets were separated from the start of the refinement. Then you use a FSC of 0.143 here to calculate the resolution. And then you have a map and a perfect model. In this case, GROW-EL, we have a PDB. Then you report a FSC of 0.5. So this is important because if, in principle, you can claim resolution anywhere. So this is happening recently in many of the papers where people tend to use, instead of one of these values, tend to use 0.25, 0.3, or sometimes 0.1 and so on, which is, again, mathematically not meaningful. So you can read. Sorry?
1.3 worth as 0.1.
So
I think 0.3 would be better as 0.1.
okay, I think
Could you explain where it comes particular 143?
why or how?
How
Where?
do you decide that
So
this
okay, so
operate
they.
why
So,
it's the best?
no, it's not the best. It's a measure. That's it. So the best. So in EM, the only way we have of estimating the resolution is just based on FSCs. So you need to decide one of these values here.
How you decided that
One-
0.143 better as anything else?
So this was derived based on a comparison between X-ray and the EM maps in 2003, and they calculated a figure of merit of I think I don't remember, 0.5 was best. That's how Richard.
0.5 is goes for the logic. If it better 1.4, cross correlation is reliable.
Yeah.
When it's lower than threshold 0.5, it means that it's less reliable. It has been shown by Joachim Frank. It has been discussed with some sort of level of cross correlation, how it's reliable or not reliable. But that I was wondering about how you can explain to us, we don't know anything. Why do you think that threshold 0.143 would be, why not 0.2?
Okay, so the way they calculated 0.143 was based on the figure of merit between the X-ray map and the EM map, which they published in 2003. So they derived a formula telling where the cutoff should be. Anyway, so what I wanted to tell you is, irrespective of what values do you use. Sorry?
I just wanted to comment that the way they determine resolution for crystallographic data is also very murky.
No, leave that alone. Yeah. Anyway, so so okay. The reason why I put these two numbers here. So whatever you do with these numbers here, when you are going to publish or when you want to show someone about your reconstruction, then you need to show two curves here, which is from the two independent half data sets and one from the map and whatever model you built. Then you need to say how good the correlation between the two halves and the map and the model. So that's what I wanted to say. So irrespective of the value, so look, 0.143 or 0.2, it doesn't matter. Okay? The most important thing that matters is that in the EM map, the resolution is not uniform. It's going to be different. So in the core regions, they are going to be better. So whatever these values they are going to tell is the overall resolution of the map. So it's always better to look at the map and then decide what kind of resolution that is, rather than which I personally don't like, because if I'm going to say I have a map of 3.8 and most of the periphery is about 6, then of course the editors will like it and they'll publish. But of course, if the biology is on the periphery, then I will not be able to interpret. So that's something to remember. Okay, so again, this is another example of beta-gal where when you do a conventional refinement using cross-correlation and without splitting the data, then you see this overfitting here, which comes as streaks here. This is overfitting, and this is where the data set was separated into two halves. And again, you can see the FSC is calculated for the conventional and the gold standard ones. One thing to remember is that even within the half maps, when you refine with RelyOn, although they are independent, you tend to get overfitting. So this is an example of a protein, of a small protein which I have been working. It's an ion channel with about 170 kilodalton. You can clearly see the protein molecule here on the detected micelle around it, but you see overfitting. Because the data sets are divided into two halves, the noise are not correlated, so you still get a reasonably good map. It's about 5 angstrom where you start seeing helices and pitches. So this is to remember that although the data sets is divided into two halves, you still get overfitting because the noise is too much in this data. So how do I know my refinement is improving? So this is an example of beta-gal where you start with a kind of a blob, which is about 50 angstrom. This is again recommended. Whenever you start a refinement, you start with something very low, just giving the shape of the molecule. Otherwise, again, you will get model bias if you start with something like 10 or 15 angstrom. So the things to remember is, of course, whether your accuracy is increasing during the refinement. So here we start in RelyOn, we start with about 999, and then in this case, we could reach about 0.9 degrees, and the resolution is about 4.5 after, say, 20 or 25 iteration. So this is to show the orientation distribution. So when you start, it's sampling in course, and then you see a lot of, this red peak means that there's a preferred orientation of this molecule here. And then as you go towards the end of the resolution, you see finer peaks here, and there is some preferred orientation, but it covers most of the molecule. Okay, so the other thing to remember, so at 15 angstrom for this molecule, you don't see much apart from a kind of an overview with some domains visible. At about 10 angstrom, then you possibly start seeing helices, and at about 7 angstrom, then you can clearly see the separation of the helices here. And about 4.2, then you can clearly see the ridges and some side chains starting to appear. So irrespective of what FSC tells you, it's better look at the map and then decide what kind of resolution you have had. Okay, so the number of particles, this can be estimated from B factors. Again, this comes from Richard Henderson and Peter Rosenthal. So they call B total, which is a combination of B image and B computational. B image means the images are not good, so you have a kind of a B factor when you are taking an image. So that is one of them. And B computational is whether you can determine the orientation of the particle very accurately. So you have two of these, which in together is called B total, which can be estimated from the map. And then you have this formula here, which you can determine how many particles you need based on the dose and the signal to noise ratio. So in the case of pyruvate dehydrogenase in this paper, which was taken on film, so it had a B factor of about 1,200, and they used about 3,600 estimate particles. It has a icosahedral symmetry. So they got to about 8.7. So I extrapolated to include some of the examples which we have been working here. And these are all with direct detectors. So there's a big jump from what we had in 2003 to what we have in 2012 to 2013 here. So these are some of the examples: number of particles, number of asymmetric unit, and the resolution we are getting. So you get a B factor from these maps. Then you can use that to calculate, if you want to go to 3 angstrom, how many number of particles are asymmetric you need. So this is useful to calculate before you start collecting a lot of data. So if in case you find that, say, for example, in the case of complex 1, if I add maybe, say, 5 times more particles, the resolution goes only to 4.5, then you need to address why it doesn't increase. It could be because of preferred orientation, or it could be because of heterogeneity, or it could be because of not optimal imaging. So orientation distribution, this I think you may have seen from Nitesh, who gave a talk a couple of days back. So this is an enzyme which is bifunctional. I thought I will use it to demonstrate what happens when you have a preferred orientation. So this is the map we got with all the particles. This is about 4.2. And then you could fit the model nicely. There are some regions which are not explained by crystallography, which you can build. So then I took only these views here, which are from the top and the bottom. And then you can see that most of the views here in the distribution is here. And the resolution is very poor. And then you can see this as anisotropic resolution. If you take the side views, the map looks far better, about 5.1. Then you get higher orientational accuracy. Although this is preferentially oriented, or there are only 2 views here, you still get a reasonable map. This just shows that for this molecule, I think these views contribute most to the reconstruction of the map. So this is something important to remember, and you get this distribution within the program as a build file, and then you can display it in along with the map to see whether you have covered all again. You do a tilt pair, which now is not probably necessary because you get high resolution, so the handedness is already known. Then you do the phase randomization. Again, this one is important only when you have a very, very low resolution map. Okay, it will come tomorrow, but I'll just tell. So the tilt pair. Okay, so he's going to explain. Yeah. Okay, so will explain, or you will see tomorrow. So in practice, some thoughts of what one should do when you start processing data. So always do 2D class averaging before you do reconstruction. This is a powerful means of cleaning the data set. So the quality of the classes directly tell how good your reconstruction is going to be. So in particular, when you are using a direct detector, you should start seeing structural features like alpha helix already in the 2D classes, which means that you should be able to get high resolution. And in most cases, any program, you start with 100 to 200 particles per class for cryo-EM. If you are using native stain, less than 50 is enough. And this is one of the things, because most proteins are macromolecules, are highly dynamic, they are machines, they tend to work. So in a given specimen, you are going to have many different conformations. This is going to limit your resolution. With maximum likelihood and classification, you should be able to classify them in most cases, but there are some cases where if the changes are small, you will not be able to do. So in this case, some biochemical knowledge can be used to determine how many classes and also to interpret if the classes are meaningful. So you have to remember that if you give the program to classify the particles into 5 or 6 classes, it's going to do that. But what it comes out, you need to interpret them very carefully. And the final thing is that smaller, high-quality data set is better than large and dirty ones. This is simply because the time in the microscope is very expensive. Computationally, they are very expensive. And with the smaller, high-quality data set, you get cleaner reconstruction. So again, with the final B factor of the map, is a useful measure for the quality of the data. So look for this value, and then try to see what goes wrong, either by 3D classification or already in 2D classification. So these are some of the papers or chapters which you can go into and read. This is just a few of the papers, but there are a lot more which will go beyond. So I think you can look into many of the references which are quoted in this in these references. I would recommend in particular this one for any beginner because it has also a lot of theory on how image is formed and why you need to restore and so on. Okay, so thank you. Yeah.
Thank you for the nice presentation. So I have one question, like when you generated reconstruction from your noise images, did you use any initial model or the same initial model as a virus?
Yeah. So the way we did, I did, this was done for different purpose. We were trying to estimate what is the real resolution in the map. So how much noise is being built by different programs. So the way we did was to pick the noise. Those are the empty regions, and then use the orientation parameters from the particles, real particles, and then do a reconstruction.
Okay.
And that way, this already tells that some of the programs you can't just refine noise.
Thank you.
Vinod, thanks for a nice talk. I just have two questions. First thing relates to the matching of the classification of the asymmetric particles where you see a good correlation, where you can say that, okay, this matches to the exact position of the particle. But if you have, for instance, say a virus which has high symmetry, obviously you don't get a similar correlation, but is symmetry itself enough to take care of that? Or
Yeah. So that's how in the old days when they were doing viruses, they didn't need to use any of these fancy programs.
Okay.
So they could use symmetry to actually build the 3D maps.
Okay. And secondly, with regards to the noise versus the picked particles that you had refined using Relion and FreeAlign, so in both instances you use the same low-pass filtered model to start off with, is it? Did you give a model? Or?
Yeah. So I gave the same model to refine.
Okay.
So so in Relion always it splits the data into two halves, but also in classification you can keep them as one common data set without separation, and then there is a parameter which you can play with where it actually overfits the data. So you can do that in FreeAlign. So the option which I didn't tell is you don't have to, there is no need to separate the data into two halves.
Okay.
So if you are aiming for say 3 or 4 angstrom, then you can limit the resolution during refinement to 6 or 7. Then whatever you get beyond that is going to be true. So that's how FreeAlign does it. So you can do that. In the case of noise refinement, I just let it go all the way to the Nyquist frequency. In this case, it was about 3 angstrom.
Thank you.
So in the previous slide, you mentioned high quality images.
Yeah.
So how do you judge, or I mean, what is the criteria? I mean, you said what would be a simple man's view of how to judge high quality images?
You look at the image, you should be able to see particles in all different views.
That's it?
Yes. If you can't see them, then you know that something is wrong. Yeah. In the sense that you need to have enough contrast so that you can pick them. If your eyes can pick, then the computer can pick easily.
Okay.
Sorry?
What about color?
the tone rings, so because we are using detectors now.
Not explain.
Okay.
This person, what was he's asking. He can see particles, he can see good distribution of angles, but still doesn't have that resolution.
Yeah.
Why?
Well, look, the tone rings. Okay. The tone rings. So when you do a Fourier transform of those images, you get rings, tone rings. So which you come from Gatan to cell K, to cell K2. The one of the tests they do is to have a platinum iridium, and so that the tone rings goes all the way to whatever resolution. So that's again a good method to check if your images are good. But again, a lot of times people use carbon as a support material to put the specimen in. So even if the particles are not good enough, if you had carbon, then of course you're going to see the tone rings going far away. Doesn't mean that the images are good.
Yeah, that's true.
Yeah. So for a trained eye, most times what we look, so when I am starting a project, I always use very high dose, like about 60 or 70 electrons, so that you can see the particles, and relatively high defocus when I am starting, so that you can see clearly what this protein in solution looks like, and whether I can see all possible views.
Yeah, I have one more question, if you don't mind. In some of the programs, you showed that you start from some, let's say, 0 iterations and go up to maybe 20 or 30 iterations, and come down to a final resolution of something like 4 or 4, whatever the number is. When you say that after the iterations, can you really mean by looking at a point-to-point resolution of 0.4, I mean 4.5 or whatever number that is? Or it's just a question of a mathematical number?
Well, so again, some of the programs are very, like Elena said, they use a fixed value of FSA to cut off.
Yeah.
And then they report this resolution at X FSC as this. But what is important to remember is that the map as a whole thing, the number that comes out after refinement is a single number.
Yeah.
It doesn't mean that the map is all uniformly X angstrom.
Okay.
So some of the core regions will be about 4 angstrom. Then you should see features which are really 4. In the case of proteins, where you see alpha helices, you should see at 4 angstrom pitches, aromatic side chains should start coming up. But however, if you look at the map, in most cases, for example, ribosomes, which have reached very, very high resolution, most of the periphery.
So is it fair to say it's an averaged out number?
Yes, it is. So that's why generally people, when they publish now, they include a what we call local resolution, where you see different colors saying that the core is X resolution, and then as it goes to the periphery, it's poorer. That's very important because for a biochemist or a other person who is looking at a EM map, he will be excited to see, oh, this looks 3.8. But when you look in the map, really, some of the regions will be very poor.
Very poor, yes.
Yeah.
Thank you.
Vinod, thanks for the nice talk. I don't know if I mistook it, but when you're showing the beta galactosidase, when you took preferred orientations to calculate the map.
No, that was a different protein.
Okay.
Yeah.
Anyway, when you have preferred orientations, I'm not sure how it affects does it entirely affect the overall quality of the map, or only specific regions of the map?
Some specific regions, because you are sampling only one particular orientation.
But the images that you showed were pretty much, apart from specific regions, they're pretty much the same.
Oh no, the regions I actually projected in the screen was so to show that the beta strands, which were separated in the whole data set, was not done in the top view.
Okay, thank you. And the other question is with respect to your SPEMS program, which you mentioned, the algorithm.
Yeah.
So could you please get back to that formula and just explain the terms in that? I sort of.
Oh, you mean how to simulate experimental images from the.
Yes.
So the SPEMS program is not publicly available simply because Greg, who wrote it, he has not finished it.
Okay.
And so what that program does is you give a PDB or in a MRC format, and then you input the parameter which you want to use in a microscope, say pixel size, voltage, number of electrons, and the defocus value. And then you can project that particular map into different projections, and then it gives an idea of how your particles should look like in a micrograph, in a microscope. But the problem is that it's very difficult to get the parameters of the detector very accurately. And that's one of the things which we find very difficult in that program.
Thank you.
Thank you for the nice talk. I just have one short question. Since you said that when we have very noisy image, we have some problem with cross correlation, find orientations and shift. So a simple way is to, I think people already done just doing the smoothing. Do you think that will be help a lot, or do you want to? Since I'm very new in this field, so do you think that will help a lot, or just will not help very much?
I don't think that helps much.
Okay.
The noise is still there in the data. It's whether you let the noise take over and get very kind of features, or whether you kind of downweight them. That's what some of the programs does very nicely.
Okay. Okay, thank
because
you.
even the half data sets will have noise in them. That's what I was saying, that you get overfitting within the half data sets. But that noise features, when you do it in, say, 2 separate half data sets, they don't correlate well. So they kind of average out.
Okay, thank you.
Okay then. If there are no more questions, let's thank Vinod for a very nice talk. You should come here. Keep that anchor. I want to give you this. This is for you.
Oh, thank you.
Sir. I am opening this because this is original one.